In 2013, a billionaire stood on a stage in California and announced that he had conceived of a revolutionary transportation system. Passenger capsules floating on a cushion of air inside a sealed low-pressure tube, traveling between cities at nearly the speed of sound. The media called it visionary. Engineers called it the future. Investors committed hundreds of millions of dollars. The name was Hyperloop, and the man was Elon Musk. What almost nobody in that audience knew, what the press did not report, and what Musk himself may or may not have been aware of, was that a small group of engineers in a country the size of Maryland had already designed, modeled, and formally proposed that exact system, not a sketch on a napkin. A full engineering study with computational fluid dynamics, detailed cost projections, geological surveys, and a working partnership with the Swiss Federal Institute of Technology. They proposed it in 1974. 40 years before Hyperloop had a name, Switzerland had already engineered the answer. And then, quietly, precisely, in the most Swiss way imaginable, they buried it. The question is not why they built it. The question is what went wrong in a country that builds everything right. But before you can understand what Swissmetro was, you need to understand the land it was designed to cross. Switzerland occupies roughly 15,900 square miles of Central Europe, slightly smaller than the combined area of Massachusetts and Connecticut. But that comparison is deceptive, because almost 2/3 of the Swiss landmass is alpine terrain, mountains rising above 13,000 feet, valleys carved by glaciers, and passes that remain snowbound for half the year. The usable land is compressed into a narrow corridor running east to west, from Geneva through Bern and Zurich to St. Gallen. This corridor is approximately 200 miles long and rarely more than 30 miles wide. Inside it live nearly 6 million of the country's 8.5 million people. The Swiss solved the surface transportation problem long ago. Their rail network is considered the finest in the world, with over 98% on-time performance and a density of track per square mile that no other nation matches. The Swiss Federal Railways carry over 1.3 million passengers per day. Trains from Zurich to Bern take 56 minutes. Zurich to Geneva takes 2 hours and 42 minutes. For most countries, this would be enough. For the Swiss, it was a starting point. In 1974, Rodolphe Neith, a Swiss engineer and professor, published the first formal concept for what would become Swissmetro. The idea was deceptively simple in principle and staggeringly complex in execution. Build a tunnel between Swiss cities, seal it, evacuate the air inside to a near vacuum at roughly 1/100th of normal atmospheric pressure, and propel a magnetically levitated vehicle through that tunnel at speeds exceeding 500 kilometers per hour. No friction from wheels, no aerodynamic drag from air, no noise at the surface, no weather dependency, no visual impact on the alpine landscape. Zurich to Bern in 12 minutes. Zurich to Geneva in under 45 minutes. The entire populated corridor of Switzerland connected at a speed that would make the country function, for practical purposes, as a single city. If you think this sounds exactly like Hyperloop, you are paying attention. Remember that date, 1974. The concept lay dormant for nearly 2 decades, kept alive in academic papers and engineering seminars at the Swiss Federal Institute of Technology in Lausanne. Then in 1992, a formal company was established. Swissmetro Incorporated, registered in Geneva, brought together a consortium of Swiss engineering firms, university research groups, and transport consultants to produce a comprehensive feasibility study. The Swiss federal government granted the project formal recognition and partial funding for research. This was not a fringe idea. This was Switzerland doing what Switzerland does, taking a radical concept and subjecting it to the most rigorous, methodical, unromantic analysis imaginable. Now here is where the engineering becomes extraordinary. The proposed tunnel would have an internal diameter of approximately 5 meters, bored through rock and sediment at depths ranging from 50 to 300 meters below the surface. The construction technique would rely on tunnel boring machines, a technology in which Switzerland already led the world. The Gotthard-based tunnel, which would later open in 2016 as the longest railway tunnel on Earth at 57 kilometers, was already in its planning stages. The Swiss knew how to bore through mountains. They had been doing it since the Gotthard rail tunnel was completed in 1882. Inside the Swissmetro tunnel, the air pressure would be reduced to between 5 and 10 millibars, compared to roughly 1,013 millibars at sea level. At this pressure, aerodynamic drag drops to less than 1% of its value at the surface. A vehicle traveling at 500 kilometers per hour in this environment would experience less air resistance than a conventional train at 50 kilometers per hour in open atmosphere. The energy savings were dramatic. Swissmetro engineers calculated that the system would consume approximately 15 to 20 kilowatt hours per passenger per trip from Zurich to Bern, roughly equivalent to the energy used by a household clothes dryer running for 1 hour. For a journey of 120 kilometers at 500 kilometers per hour, that is an almost absurd level of efficiency. The vehicles themselves would seat between 200 and 400 passengers, levitated by electromagnetic suspension and propelled by linear induction motors embedded in the tunnel guideway. There were no wheels, no pantographs, no contact between vehicle and infrastructure. Acceleration and deceleration would be limited to a comfortable 1.5 meters per second squared, comparable to the sensation of a commercial elevator. Passengers would feel almost nothing. The ride from Zurich to Bern would involve roughly 3 minutes of acceleration, 6 minutes of cruise, and 3 minutes of braking, a remarkably comfortable trip. The total estimated cost of the first line connecting Geneva, Lausanne, Bern, and Zurich was 25 billion Swiss francs in 1998 estimates, equivalent to roughly 18 billion United States dollars at the time. The network would eventually extend to Basel, Lucerne, and Lugano, creating a national grid with a total estimated investment of between 50 and 80 billion Swiss francs. Stay with this because the numbers are about to get very interesting. The feasibility study projected that Swissmetro would carry between 14 and 20 million passengers per year on the core Geneva to Zurich corridor alone. At a ticket price competitive with first-class rail, estimated at between 40 and 60 Swiss francs per trip, annual revenue would approach 1 billion Swiss francs. The operating costs, thanks to the extraordinary energy efficiency of vacuum maglev transport, were projected at a fraction of conventional high-speed rail. The study concluded that the system could achieve operational profitability within 15 to 20 years of full service, a timeline that is aggressive but not unreasonable for major transport infrastructure. The engineering was peer-reviewed by faculty at the Swiss Federal Institute of Technology, by the Swiss Federal Office of Transport, and by independent consultants. No fundamental physical or engineering obstacle was identified. The technology for magnetic levitation existed. The technology for tunnel boring existed. The technology for vacuum pumping existed. Every individual component of Swissmetro had been demonstrated in other contexts. The challenge was integration, building a system in which all of these technologies function together, reliably, safely, and at scale. And this is where the dream began to fracture. In 2009, the Swiss Federal Council formally declined to fund further development of Swissmetro. The stated reasons were financial and political. The capital cost of 25 billion francs was enormous, even for a country as wealthy as Switzerland. The existing rail network, already among the best in the world, was undergoing its own multi-billion franc expansion under the Rail 2000 program. Political appetite for a speculative mega-project, however well engineered, was simply not present in a nation governed by consensus, referenda, and a cultural instinct that favors incremental improvement over revolutionary leaps. There was also a deeper, quieter objection that engineers close to the project have discussed in the years since. Switzerland is a country that defines itself in part through its landscape. The Alps are not merely geography. They are national identity. The idea of boring hundreds of kilometers of tunnel beneath that landscape, even tunnels that would be invisible from the surface, generated a philosophical discomfort that no feasibility study could address. Swissmetro was technically sound, financially plausible, and culturally uncomfortable. The company continued to operate on a minimal budget through the 2000s, publishing updated studies and seeking private investment. But without federal support, the project could not attract the capital required for a prototype, let alone a full network. In 2011, Swissmetro Incorporated was quietly dissolved. Think about the timeline for a moment. The concept was published in 1974. The company was founded in 1992. The feasibility study was completed in 1998. The government declined funding in 2009. And in 2013, 4 years after Switzerland said no, Elon Musk published a 57-page white paper describing a system of passenger capsules in a low-pressure tube traveling at high speed between cities. The media treated it as an invention. It was a rediscovery. Hyperloop 1, later rebranded as Virgin Hyperloop, raised over $400 million in venture capital. It built a 500-meter test track in the Nevada desert and conducted a single-man test in 2020 at a speed of 107 miles per hour with 2 passengers. The company laid off most of its staff in 2022 and pivoted to cargo only. Hyperloop Transportation Technologies, another competitor, has yet to carry a single passenger. As of today, no Hyperloop system anywhere on Earth carries paying customers. The technology that Switzerland engineered to completion on paper in the 1990s remains, 3 decades later, unbuilt by anyone. The Swiss Federal Railways still run at 98% on time. The Gotthard-based tunnel carries passengers beneath the Alps at 250 kilometers per hour through 57 kilometers of rock. Switzerland continues to build the best conventional rail infrastructure on the planet, precisely, methodically, on schedule, on budget. Somewhere in the archives of the Swiss Federal Institute of Technology in Lausanne, the complete Swissmetro feasibility study sits in a filing cabinet with its computational models, its tunnel cross-sections, its passenger flow projections, and its energy calculations that showed a nation of 8 million people could have been connected at 500 kilometers per hour for the energy cost of running a clothes dryer. The engineering was never the problem. The physics was never the problem. The money was available. The expertise was unmatched. Switzerland simply decided that the future could wait. And by the time someone else tried to build it, they discovered what the Swiss had known all along, that the hardest part of a vacuum train is not the vacuum, not the magnets, not the tunnel. It is convincing a civilization that the ground beneath its feet is not sacred.